Today in this video, we will see numerical on shear stress distribution diagram. Numerical is a simply supported beam of 4 meter carries uniformly distributed load of 80 kN per meter over the entire span. Draw the shear stress distribution diagram at support indicating all important values in this figure. This is T section of simply supported beam with flange width 150 mm, flange thickness 50 mm, web thickness 50 mm and web depth 150 mm. And to find shear stress distribution diagram. So first step for solving this numerical is first to find position of neutral axis y bar. Let us consider this wave as 1 and flange as 2. Y bar is equal to a1y1 plus a2y2 upon a1 plus a2. A1 is this wave portion area 50 multiplied by 150, 7500 mm square. Y1 is position of neutral axis for that wave portion, only wave portion 150 divided by 2, 75 mm. A2 is area for that flange portion 150 multiplied by 50, 7500 mm square. And Y2 is position of neutral axis for that flange portion from bottom fiber, extreme bottom fiber 150 plus 50 by 2, that is 175 mm. Put these values in y bar equation. Y bar is equal to 7500 multiplied by 75 plus 7500 multiplied by 175 divided by 7500 plus 7500 is 125 mm is position of neutral axis from bottom fiber to that T section of simply supported beam. Now next step is to finding moment of inertia. Moment of inertia for that whole T section is something here, and this is x-axis, and from bottom fiber distance is 125 mm. And for calculation of this moment of inertia about centroidal axis for the T section, first consider moment of inertia only for that wave portion. Only for that wave portion moment of inertia is somewhere here 75. x1 and for flange portion moment of inertia is here x2 axis. So first calculate this I x1 moment of inertia. I x1 plus I x2 x2 I is equal to, for that wave portion, 50 multiplied by 150 cube divided by 12, plus area of that wave portion 50 multiplied by 150 is 7500, and distance between original neutral axis to that x1 axis is 125 minus 75 is 50, and square of this distance 50 square, plus now moment of inertia for flange portion I x2 axis, 150 multiplied by 50 cube divided by 12, plus area for that flange portion 7500, and multiply by distance between x2 axis and x axis is 175 minus 125 is also 50 mm, and square of that. Now first curly bracket is 7500 multiplied by 50 square plus 50 multiplied by 150 cube divided by 12 is 32.81 into 10 raised to 6, plus the second curly bracket is 7500 multiplied by 50 square plus 150 multiplied by 50 cube divided by 12 is 20.31 into 10 raised to 6. Therefore, this moment of inertia is 32.81 plus 20.31, 53.12 into 10 raised to 6 mm raised to 4. This is moment of inertia for that T section about x axis. Now next step is to calculating stresses at junction and stresses at neutral axis. Stress as extreme top and extreme bottom is 0, shear stress. Now calculate shear stress at junction. Junction, that means at this point, at this portion. Now area above junction A. Area above junction, that means area for that flange portion. Area above junction is 150 multiplied by 50, 7500 mm square. And CG of area above junction with respect to neutral axis. CG of area above junction with respect to this XX neutral axis is This total distance is 150 plus 25. This distance is 175 mm, and minus this distance from bottom extreme fiber to x axis distance minus 125. That means 50 mm. This distance is 50 mm. And so CG of area above junction with respect to neutral axis is 50 mm. Width at junction for that flange portion width denoted as B1 is this 150 mm. Width at junction small b1 150 mm and b2 for that this portion b2 is 50 mm. This b1 is 150 mm and b2 is 50 mm. Now next formula for that shear stress distribution is tau1 is equal to SAY upon B1I. This S is shear force, and shear force for that simply supported beam is WL by 2. W is 80, L is 4, length of beam is 4 and divided by 2. That means 80 multiplied by 4 divided by 2 is 160 mm. Sorry, this is 80 is in kilonewton per meter, 4 is in meter. This meter get cancelled. This shear force unit is in 160 kilonewton. That means this S is equal to 160 into 10 raised to 3 Newton. 160 into 10 raised to 3 Newton multiplied by area of that flange portion 150 multiplied by 50 7500 multiplied by y is this distance, neutral axis distance 50 mm, divided by b1 is this 150 mm, and I moment of inertia 53.12 into 10 raised to 6. So 160 into 10 raised to 3 multiplied by 7500 multiplied by 50 divided by 150 multiplied by 53.12 into 10 raised to 6 is 7.53 Newton per mm square. is shear stress at junction and tau 2 shear stress at junction and at width at this 50 mm B2. For this 50 mm B2, shear stress tau 2 is SAY by B2I. This S is same 160 multiplied by 10 raised to 3. This area is, sorry, this for calculation of this tau 2, we directly use this formula. Tau 2 is equal to tau 1 into B1 upon B2. Tau 1 is 7.53, B1 is this 150 mm, and divided by B2 is 50 mm. 7.53 multiplied by 150 divided by 50 is 22.59 Newton per mm square. This is tau 1 and this is tau 2. Now next calculate stress at neutral axis, shear stress at neutral axis. Same formula, tau max is equal to SAY upon BY. This S is also same 160 multiplied by 10 raised to 3. Area is, for calculation of shear stress at neutral axis, this area is below this neutral axis area. That means this neutral axis is at a distance of 125 mm from this extreme bottom fiber. That means 125 multiplied by this 50 mm thickness is area 6250 mm. And Y is centroid for that much portion, that up to this x axis from bottom fiber. This is 150 divided by 2 is centroid. Sorry, 125 divided by 2 for that much portion. See, here something, here x axis. For this portion, centroid is 125 divided by 2, somewhere here. And divided by B. B is this 50 mm and I is 53.12 into 10 raised to 6. This is maximum shear stress at centroidal axis for that T section is 125 divided by 12 multiplied by 6250 multiplied by 160 multiplied by 10 raised to 3 divided by 50 multiplied by 23.53 Newton per mm square. Now see shear stress distribution diagram. This is cross section of beam. Shear stress distribution diagram. This tau 1 is 7.53 Newton per mm square. And tau 2 is 22.59 Newton per mm square. Here tau 2. These both stresses are at junction. See here. And at neutral axis, stress is maximum 23.53. Here 23.53 Newton per mm square. So this is shear stress distribution diagram for that T cross section of beam. At neutral axis 23.53 shear stress, and at junction 7.53 and 22.59 Newton per mm square. Thank you very much.